This is Free Range Digital Design Foundation Modeling. This is Chapter 14, Lecture number 2. We've been dealing with mixed logic. Previous lecture gave a giant overview, and we'll go through some review in this lecture, but mainly we're going to get to do some design and analysis problems. But particularly, we are going to do analysis problems. Recall that mixed logic is essentially a matter of a digital circuit that has both a negative and positive logic in it. Once again, negative logic means 0 is the action state, and positive logic is when 1 is the action state. So we have two ways to indicate and work with negative and positive logic or mixed logic. We can use the positive logic convention, which uses these overbars to indicate negative logic. But more importantly, what we're going to use is the direct polarity indicators, where this H here represents a positive logic signal and the L represents a negative logic signal. There are two main tools that we're going to use to do design and analysis. One of those is the fact that we're going to use this equivalent signal. So there's these equivalent signals give us an alternative way to write signals. Okay, we're going to use this because it's going to help us match logic levels in such a way that we can read off the answer once we get all the logic levels matched, and we have 100% confidence if we match the logic levels that the values, the equation we read off is going to be correct. Equivalent signals is one approach. The other approach was to use equivalent gates. Now, the notion behind equivalent gates is there are two forms of AND gates, which are these two forms. There's two forms of OR gates, which are these two forms of NAND gates, which are these two forms, and there's two forms of NOR gates, which are these two forms. Okay, so we can go back and forth between these forms. Most important thing is we're going to use the gate that's most appropriate to the function that we're actually executing, particularly that the gate's executing. Now, the issue is, since we have different gates, for example, these are NAND gates, since we have different ways to represent NAND gates, which way is the right way? So here's just some circuit here. Nothing special about this circuit, but it looks a little bit confusing simply because, I mean, it's all NAND gates, it's not that confusing. But it's a little bit confusing because essentially these logic levels don't match. I have bubbles here. I'd like to see bubbles there. That would make me happy, but give me the warm and fuzzies, but I don't see them, so I'm not comfortable with this. But the better way to write the circuit is not this form, but in this form. The difference between these two forms is we've replaced that NAND gate with this form of the NAND gate. Now the issue is these are essentially AND OR forms, which are SOP related forms, and so it's actually doing an OR function there. So I'm going to draw that gate as an OR function. Remember, it's AND OR. These are the ANDs. That's the OR. The nice thing about this circuit is it's drawn in such a way that interior logic levels match, and this is referred to as famous bubble matching. And also this has a positive logic output, and there's no bubble on the output. This is a positive logic output, but there's a bubble sitting there, and it makes me think, wow. Or like when you see that in a circuit, you think to yourself, is that what the person meant to do, or did the person make a mistake? So these are both valid circuits, but this is the better way to draw the circuit. And you can say the same thing for the NOR forms, which come off of OR AND, which are related to POS forms. So this one's okay, it's just a little bit confusing. I see a bubble there. I would like an F bar there, but I don't see that. This is the better way to draw this thing. It comes from an OR AND form. So these are the ORs, here's the AND, so I'm going to draw it that way. And once I draw it that way, I see these bubbles match, and I see this positive logic output matches the output of that OR gate, which is actually it's an OR gate. So more on that later. This is actual better way to draw these circuits. This is our first example, and I have a circuit there where the output is not stated, So this output B, we're going to do this for positive logic and negative logic. Well, let's do the positive logic. Okay, F positive logic, this A, what I'm looking for is F sub I equals what? But the way this is drawn is this is F sub I right here, looking good. Because this is a positive logic, I want to put a gate there that has positive logic output, and this AND gate just so happens to have a positive logic output. So I don't have to change that gate, which is good. Now the other thing is this gate here has positive logic inputs, so I want to make sure these inputs match the logic levels of the gate. So this gate is expecting positive logic, and I'm giving it positive logic. So here we go, this is a positive logic B, goes through an inverter, becomes negative logic. Not very comfortable with that because this expects positive logic, and so I'm going to change that to B naught sub high using equivalent signals, and this signal's B naught sub high, and so I have an A high and a B naught sub high, and I can write the equation from that, which is going to be F sub high. I will take a shortcut here, A B naught sub high. Okay, I could put the polarity indicators on these inside variables, but I opt not to, just to keep it clean. It's understood that I've matched all the internal stuff. All I'm interested in is the outside. These necessarily match. If they didn't match, it would actually make no sense. B is negative logic, F sub low, F equals what? I would like to have a circuit, a gate here that has a bubble on the output. Now I can't change the circuit, but I can use an equivalent gate. So this is an AND gate. There so happens to be another form of an AND gate with a bubble on the output, and it looks like this, and there's my F sub low. Now what I've done is I've matched that logic level of the out stated of the variable with a bubble. That's going to allow me essentially to read this off once again. So looking good here so far. Let's make sure these logic levels of the input to the gate match. I have a positive logic going into a gate that expects negative logic. Obviously that's not going to work. I can't add an inverter or anything like that. What I can do is use an equivalent signal here. A sub high, A sub positive logic is a barred A negative logic, and there's that right there. Good, so this is a B sub high, positive logic goes through inverter, it turns into negative logic, there it is. So this gate, I've got the output negative logic that matches the bubble. This gate expects negative logic on the input. This signal I rewrote as negative logic using equivalent signals. And this input here essentially went through an inverter, and after it went through the inverter, it became the proper logic level. And I can read these off. F sub low equals A naught, which is directly read off this thing, and it is a OR gate here, A naught or B. And that's my final solution here. Once again, these lows match. If it didn't match, it would make no sense. This is another problem. It's similar to the last one, but I've got different values on the inputs, and it uses different gates. So let's do positive logic. A, so I'm looking for F sub high. So if I look at this gate, I see it's a NOR gate. I can't change the gate, but I want to write this gate such that there's no bubble on that end of it. And so what I'm going to do is use an equivalent gate. And here's the equivalent gate. This is the AND form of a NOR gate. Switch the gates, and I have to fill in these guys. I can't really add anything. This is a gate that expects two negative logic inputs, so I have to make sure I give it negative logic inputs. Once I do that, I can read directly off the gate. It looks like it's the gate that's performing an AND function. So this is going to be B sub high, B sub low, and so I've got a negative logic there, it matches those logic levels, and I can read this off. F sub high equals A and B. Remember this AND comes from this gate here, so I'll erase that now. And B and it is active high. F sub low, I want to see a negative logic output. It's already looking pretty nice as is for negative logic because I have that bubble there that matches. I don't think I'll redraw this one. I'll leave it as is. This is A sub high. This gate here expects positive logic. I can't add an inverter, but what I can do is use equivalent signals to write that in a positive logic form. Looks like a B sub positive logic. Here we go. Goes through an inverter, so it becomes B sub low, and that's not good enough because this thing expects positive logic. This is going to be B naught sub high. So I've written these two signals in positive logic form because that's what this gate expects. If I give it two positive logic signals, it will perform an OR function. So I'm ready to write the answer to this thing. So it's going to be F. And that's the answer to B. So this one is a bigger problem. Once again, it's similar to the other ones, but there's more stuff I need to do. These problems now have multiple solutions, which I'll just do. I'll do one and I'll point out the other one. Okay, so here we go. So positive logic, it isn't going to fly in this thing because I got that bubble there. So what I need to do is redraw the gate such that there's no bubble in the output. So I can't change the gate, but I can use an equivalent gate. So the equivalent gate is going to, so this is a NAND gate here, and here's my NAND gate here. That's the F sub positive logic I'm looking for. Okay, so once I do that, the input to this gate expects negative logic, but these gates here are providing positive logic. I want to match the bubbles on these things, so I want to change these gates also to some equivalent gate. Equivalent gate I'm going to change that to is an AND gate with bubbles all over the place. Once again, these are OR gates, but it happens to be the AND form of the OR gates. I did that because now these interior bubbles match, which makes everything happy. I don't have to worry about it. So A to below goes through an inverter, and I'm going to take a shortcut here. It's going to be A naught sub low, B sub high. I need to write an equivalent signal, and that's going to be B naught sub low. And C sub low is negative logic, which is what this thing expects, so I don't have to do anything to that. And D sub high isn't in the right form, so I'm going to rewrite this as D naught sub low. Okay, so once again, these gates here expect negative logic inputs. So there's negative logic, negative logic, negative logic, negative logic. Once I do that, I can read off the answer. So this is going to be F. These are AND functions, A naught, B naught, being ORed together with this OR gate here, and this is going to be C or D naught. So I just put square brackets there. Okay, I'm going to check and verify this is right. Yeah, looks fine. Alright, hope that's okay. So the negative logic is a little bit easier. It's already written in a form. I have a bubble on the output. The inside logic levels already match. I don't really need to change that at all. What I need to do is rewrite these input signals using equivalent signals to get what I need on these things. So let's do that. Here's A sub low. Negative logic becomes A sub high. That's good. B is already high. C sub low. It's not right. I need to rewrite this as a positive logic signal. Some C naught positive logic. So D sub high goes through an inverter, becomes D sub low, which is not good enough. I need to write it as a positive logic signal, so this is the signal I'm going to use. So once again, these two OR gates here expect positive logic inputs. I've ensured that I'm getting positive logic inputs. There's 1, there's 2, there's 3, and there's 4. And once I have that, I can read off the answer here, and let's do it. F C naught or D naught. Probably should put some square brackets on that, and low. So looking at these equations, I expect to see some similarities in these things, and I don't see that. And the problem is, looking back on this, I made a couple mistakes on this thing. And the idea here is that's not an OR, that's actually an AND function. But I forgot the inverter, I forgot to draw the inverter. So this becomes D sub low, and this is a D. And once I do that, it's actually right. So once again, I hate to put that mistake in there, but I think it's instructional that I read back through this thing and found the mistake. Yep, sorry about that. Nothing's ever really perfect the first time through, but design is circular, iterative. You don't really necessarily go from the start and always get the answer first time through. Well, that's my justification anyway.